Okay, in the estimate phase. So we've done the prediction model part. Now we're actually talking about how to use that prediction model in the future to estimate a causal effect. As we've talked about doing this, and I just mentioned it again. So simple substitution estimator is what I just described, okay? Why do we need alternative estimators? And we'll talk a little bit about biased variance trade-off, not for the prediction now, but for the causal effect of interest. That's a different variance bias trade-off. Like I can do a really great job with the model for prediction. That does not guarantee that model is going to be do a great job for estimating the causal effect. And I'll give you some intuition for why that's the case. And then why do we need a new estimator? Well, one, as I mentioned, we want to get inference, and at this point, there's actually no way to get reliable estimates of how variable it is, no reliable standard errors. We'll talk a little bit about asymptotic linearity and influence curves. That's the basis for deriving theory for estimators and also for deriving new estimators. I'm not going to go deep into that. Those of you who are a biostat are doing this in 240A and getting it in a much completer form, but I'll just give you some idea of how we actually can derive a central limit theorem for an estimator and get the standard error. And talk a little bit about the non-parametric bootstrap, which is thought sort of like, I like the non-parametric bootstrap because it's sort of the mindless solution to anything, but it actually doesn't always work. And in this context is one of them, where it doesn't give you reliable inference necessarily. And chapter 5 is really the best target. That's the book, and I'll make sure to link that in the pages. So now we're shifting our focus from getting, the best model of the regression, this part, to getting the best estimate of this thing here, which uses that obviously, but isn't the same thing. To get this, the substitution one, we plugged in estimates of these things, and then we took an average over the W's, which we just use the empirical. We just take 1 over n, give every observation weight in, and take the average across all the observations. That's our estimate of this thing right here, which is the distribution of W. So we just mentioned how to get this thing estimate in the last lecture, and then you can just plug in these estimators and get this, right? That's all. I just have to plug in. It's not a terrible thing to do. Makes some sense. Probably better than doing something that relies on a biased model. I could get an estimate of the prediction, get everybody's predictive value, keeping their W and changing their A to 1, keeping their W, changing their A to 0, take the difference of those, and take the average of that differences, and that gives me an estimate of this parameter right here. So you can do that. But the problem is it's the wrong variance bias trade-off. And there's no way to get valid statistical inference for that estimator, which is why we can't just stop there. Again, how bad it is going to be a function of sample size. Again, if you have a very large sample size, such that every time I would take an equivalent sample size, a new study from the same target population, and end up with the same kind of functional form for my predictor, so that model variation, it goes away as sample size gets large, then at that point maybe I'm okay. But you never know if you're okay until you're okay. And therefore you want an approach that does a good job regardless of the sample size. So it's the wrong variance bias trade-off. And I give you a little intuition. I can have, let's say, W's in there in my potential confounders that really do confound. So having them in and out changes the estimate somewhat of the causal effect. But adding them doesn't do a great job, doesn't really help in prediction very much. They may be marginal predictors as ways of using other variables. So when I do like stepwise regression for a finite sample, it may get rid of W's that are real confounders. And therefore it's doing a great job of prediction, but it's going to now start to have a biased estimate of the causal effect. Again, that contradiction also goes away as sample size gets large, but for finite samples, because it's going to have to make some variance bias trade-off for prediction, it may make the wrong one for explanation, for the estimate of the causal effect. And that's why we need approach that won't make that error. Yeah, sure.
So by wrong bias variance trade-off, are you saying that if we were to just use this predictor that we get a superlearner, we use empirical with a P0, and then the
Could be both.
Or
Yep.
it's
It's
data
generally a
set
bias,
specific?
it's a bias problem,
The bias is too
large,
large.
in the estimate of the effective interest, right?
Okay,
So you're gonna do something which could increase the variance, but it's gonna be a targeted bias reduction step. Ultimately, we'll get to that, but, you know, that's the problem with the variance bias trade-off. It's really bias is what I'm talking about.
okay.
Yeah, I mean, so it is a trade-off, but it's making a trade-off for prediction, and it's not the right trade-off, and it's not right in a particular way, and that the bias will be higher than it should be.
Okay, so it's like too variance specific, like focused.
Yeah,
Okay.
exactly. I mean, it's really not focused on the parameter at all, but just as a consequence of not focusing on it, the variance is really controlled at expense to the bias.
Okay.
I guess that's the best way to put it. Here's an obvious one. If I do the stepwise procedure, it could be they take out A, right? If I'm doing a stepwise regression, those are all my candidates, then what's going to be the estimate of the plug-in estimate of the causal effect? Exactly 0, right? You can tell right there's going to be a problem because in repeated samples, I'm not going to have the smooth distribution of estimates. I'm going to have it's going to be like potentially, I could have something that's close to the null. It's going to be like, here's 0. I can have a bunch of ties here, right? I'll just make this like a histogram. And this is theta pn, right? And can have it's obviously not going to be normal if I can have a perfect 0, right? You're going to have a weight at one observation, so it's not going to be normally distributed. I know my inference, therefore I can't derive a limit distribution, a normal limit distribution, in order to get inference for it. So that's going to be a problem. That's an obvious one. I want something that, you know, your estimator, for it to behave in a way that I can get measures of uncertainty, it has to be that if I change the data a little bit, I don't get drastic changes in the parameter estimate. It has to be smooth with regard to the data generating distribution. So I had little errors, let's say, to every weight probability of the joint distribution of A, Y, and W. I don't want the estimate to suddenly change drastically. That's a bad sign for the estimator. It means it's not smooth in that. And this is the one way it could be not smooth. I change a little bit, it goes from not 0 to exactly 0, right? And it could be that sometimes it chooses A, and A is a big coefficient because it's highly correlated with W in some regression. And then in another one, it drops A because it uses W's that it dropped in the previous one. That's going to be a huge jump in the estimate for maybe small changes in the data. And that tells you there's a problem in the estimator. That's not going to work to have the properties we want. That's another one. It could just, again, it's exactly what I just said. So, you know, it could be the best variance bias trade-off for the prediction, drops A. Right? That's not implausible at all. That's going to be terrible for estimating the effect of A because of that problem that it's going to have a point mass at 0 when repeated experiments, because that can happen, and there can be ties now. Once there's ties, it tells you it's not normal, and we don't want something like that. You can just force the superlinear to keep A. There is ways of writing it so it never drops A. Then you're not going to get that better, you know, that's going to get rid of that problem, but it still doesn't answer all problems. So you need another approach. That's basically the bottom line. And generally, you want an approach that, you know, when you're developing an estimator, and you have a particular statistical model and a data type, you want to go through a sequence of steps that says, given that I want an estimate of this, and this is my statistical model, what is the best estimator? And for what estimator can I derive a limit distribution, a central limit theorem for? And so that's going to be different depending on what I'm trying to estimate. Not always going to be the same procedure, estimator, that will give me the best thing for everything. This is a real sort of split with that thing I mentioned previously, where you use one approach that does everything for you. It gives you a prediction. It gives your variable importance measures, those estimates of the causal effect by those coefficients in something like a stepwise regression or lasso or whatever it happens to be. That's completely untargeted, we would say. It's not making the procedure do the best job at one thing. It's trying to make a procedure that's ad hoc and you can get everything from once. And it can't do, it can't do a good job really in anything, but it satisfies all those goals simultaneously in a sort of spurious way. And the general approach we're teaching in this course, and more so in the division, is if I have a particular parameter of interest, I want to create an estimator that does a good job there. And estimating the prediction is not the same as trying to get a measure of the causal effect or the variable importance, whatever you want to call it. That's a different job. And we need a procedure that does that well. So if I want to have both a prediction model and I want to say what's important in that prediction model, those are two different things, and I want to do them separately. I don't want to get them from the same procedure because I know they won't be optimal. I can't use the same thing that will be optimal for everything. That is sort of a goal in a lot of research right now, is to come up with these big deterministic models that will do a good job both describing the system so that you can look at them and they give you some insight and then they'll predict well in the end. And I think in many cases that's a fool's errand. It's just going to do a bad job at everything. Sometimes it's helpful to have simplified models because they give you some idea of structure, but you really need to separate out specific scientific questions, separate out estimators to target each of those. And again, that's a very different kind of approach. When we do variable importance, we don't just fit, we end up fitting separate procedures for every variable. Even though we have a prediction model, we're reporting the importance for that prediction model. We don't do them together because we know it's non-optimal. We know we can't get inference we can trust for them. And so that's basically what this slide is saying. It's like, there is a set of theoretical steps you can take. We know it works well in practice, and you shouldn't have procedures that try to do too much for one procedure. They're useful exploratory tools, there's no doubt. Things like heat maps or cluster diagrams can really be informative and help you. And I'm not against those, but when you're trying to estimate a particular parameter or get variable importance that's reproducible and you can trust, or estimate the causal effect, these procedures don't do that. I've just gone over this, right? So the basic problem, as Mary just pointed out, is that the estimate of this will be biased because, and you can see it in just the example I gave. It won't be centered necessarily around, let's say I have a true causal effect of A that's close to the null, close to 0. Let's say it's like 0.01. And I don't have a procedure that targets it. I'm going to get that point mass at A at 0, and that's going to pull the estimate in the wrong direction. It's going to be biased, right? And sample size may help and it may not help in some of these circumstances. If I have procedures that don't sort of adjust to the sample size in the way that I need them to adjust to get an estimate of A, then it doesn't necessarily mean sample size is going to get rid of the problem. It generally helps, but not always. So we're going to ultimately talk about how to take and just modify this prediction model to get an estimate that has the properties we want, called TMLE, Targeted Maximum Likelihood Estimators. They are substitution estimators, so the general form stays the same. We just have to alter the regression to get a one bias reduction step, basically. So, and essentially what we're doing is reducing the bias because it wasn't targeted, and secondly, we're smoothing the estimator to make sure the distribution isn't too bumpy. It's symmetric, it's normal. And we can drive inference for it. So that, we'll get to that. We're not getting there yet. The other thing is how to get the variance estimate. When you do this procedure, if I do this procedure based on, based on a simple linear regression model that's fixed, I can get inference in that case. If I believe that model is true, and let's say it's just a linear model with no interaction terms, then the estimate of the causal effect as defined here you know, let's say it's an estimate of E y1, 0 minus E y0, y0. Then then I can get inference for that because it's simply the coefficient in a regression model. It's going to be, you know, if my model is y is equal to beta 0 plus beta 1a plus beta 2w, you know, we'll just say plus an error for now, then I know that the standard error for beta 1 hat is going to be the standard error for this PN in this model, right? It's going to be the same. I can just get the I just coefficient as an estimate of the causal effect, so I can get the standard error from linear regression. That all works fine. Anytime it starts to be adaptive, it's unclear what I do. If I'm getting a prediction from a superlearner model, and it's a combination of random forest and trees, I have no idea, right? It's not clear how you get standard error from that. So only in the extreme case of fitting a simple pre-specified parametric model can you get inference using traditional methods and traditional approaches that are based on maximum likelihood. The type that you would learn as a first year master's in biostat. When you take the stat courses, you learn all about maximum likelihood estimation, how to get inference in general. So whether you're doing logistic regression or you're doing Poisson regression, whatever it happens to be, the same principles apply. But we're getting away from that because we're trying not to assume models. Therefore, that easy route to the inference goes away. And we can't just use parametric models and the variance estimates of the coefficients and maybe the delta method, which you may or may not know, to derive those. We have to do something else. And we want to do it because in the end, you know, this is our goal. I mean, generally, as epidemiologists, we don't like this so much. If that's what you're doing, hypothesis testing, we know its limitations. The null's never true, for one, and so the p-value always goes to 0 if sample size is large. It's really this. We want to get confidence intervals we can report and are trustworthy. So they really are reporting the uncertainty of our estimates. Otherwise, we're going to get decisions that are not based on actual knowledge. And I'm gonna stop here. My throat's just killing me. I think I've got something going on. So I'll just ask if there's any questions.
Do we want to be doing this for RCT as well as observational?
That's a great question. Yes. Yeah, it turns out the simple substitution estimator and an RCT, which we won't be able to understand until we get to TMLE, is protected even if you get the model wrong. Even if you get the model incorrect, you're still protected. Therefore, you can get a reduction in variance, you know? It's not biased, right, because you're unbiased anyway in a trial by just getting the mean of y in one group versus the mean of y in the other group. And in fact, you can adjust for covariates in a way where you're only still relying on the same randomization. And it's hard to show it unless you learn TMLE first, but it becomes obvious when you look at the TMLE estimator that in fact, you can gain a lot of power in trials if you have good predictors of the outcome at baseline. And you could have much smaller sample sizes and more efficient trials. Not done very often, but it can be, and it's certainly, it probably will be done more in the future. Yeah?
So when we average across different algorithms based on their coefficient, so before that, we need to standardize all the variables?
No.
No?
No, because it's standardized to give you a prediction at the right scale. You have to make sure your prediction model is giving you a prediction at the scale of the y, right? So if it's a binary outcome, you want to make sure your predictors have some kind of logistic form or whatever it happens to be, or just turn out to be local averages, because that'll work as well, right? And we will talk about, well, maybe it's not so causal too, but ways that if you have bounds on any outcome, you can always guarantee your prediction follows those bounds. That's what you have to get right. But how you put your variables in doesn't matter. Does not matter. You can standardize them or not standardize them. That may actually not matter in terms of prediction, and if it does matter, superlearner will choose the one that's better, right? So, okay. Go and be prosperous on Pi Day.
Oh, right.
All right. Just skipping to here. I essentially did that. So anyway, the procedure again is you have, literally you have this, matrix of data, like a spreadsheet. The rows are the observations, the columns are the variables. You have some algorithm, just some black box thing that you put that data in and it spits out a number, right? That's gonna be your estimator. The Bootstrap works by randomly selecting rows in that original spreadsheet, the same, with replacement, the same size as the original data, because you're trying to mimic the estimation in samples of that size. There are variations where you take fewer and more, and there's all kinds of variations that we're not gonna get into, but for now, just the same sample size. You redo the estimator, store it again, get that one number by plugging that new data into that black box, and you do that, let's say 1,000 times, you get 1,000 numbers. And you can both just graph their distribution to get it's an estimate essentially of the sampling distribution. Hopefully it looks normal. And also you can use that to get estimates of the confidence interval. And there's various ways to get that from that Bootstrap distribution. You can do it by just getting the standard error and assuming normality, just using a typical estimate plus or minus 1.96 times the standard error, or you can get the quantiles of the sampling distribution. There's modifications of that to try to account for some bias in very particular circumstances. So it has a long literature, but the basic idea are those two. You can take the standard error by just taking the standard deviation of the estimates and using the standard walled kind of confidence interval estimate plus or minus 2 times the standard error. Or you can use the 2.5 and 97.5% quantiles of the actual distribution and choose those as your confidence intervals. And there's some circumstances one will work better than the other. Thing about so that's one thing. There you go. And you repeat this process B times. I said 1,000. It's sort of a minimum number. To certain circumstances, you might want to use more. You're really trying to get the distribution to converge, and that's just a number of computer samples. It's not a function of the sample size. You want to make sure if I did 1,000 more that my distribution of estimates doesn't change very much. So at some point, you don't gain by doing more and more. And 1,000 of roughly what people often use, and that is found to be sufficient to estimate, let's say, the standard deviation of the estimates. But there's no limit on that. You could do 1 million. The more the better, generally. The gold standard would be 1 billion. You can do 1 billion, but you're hoping that you can approximate the same thing by doing something that takes a lot less time, like 1,000. And this is how you calculate your variance, but really it's just the sample variance, right? Here's the average of the estimates, and you hope that would be equal to at least close to the estimate on the original sample, right? That's the idea. And then you're just taking the observed one minus that, squaring it, take the average. That's just a sample. It's not the sample variance. It'd have to be B minus 1, but who cares? If B is 1,000, it doesn't matter. So that's just the sample variance. Here is like an estimate of the average of the bootstraps. Sometimes this can be used in certain circumstances to look at bias. You can compare that mean versus the mean you got in the estimate you got in the original data, and that can be an estimate of bias. That's not true in the kind of estimators we're looking at, but in simpler circumstances that will work. And as I said, there's a couple ways to get the confidence interval, including the standard walled method by just getting this right, using this right here, right? The standard error is just the square root of that variance. So that's the bootstrap. I love the bootstrap because it's mindless. I don't have to think about it, right? I have an algorithm that spits out a number. I've got data. I randomly sample. I get my estimate, and it's robust in the sense that it's a non-parametric estimate. Doesn't rely on any kind of modeling assumptions or anything in particular. Maybe you're getting a confidence interval for an estimate that isn't interesting because it's not converting the thing you want, but it's getting it for whatever that thing converges to. And it doesn't require a lot of, thinking on your part to implement. It's very easy to implement. I mean, the way it implemented in R and SAS and STAT are all very similar. You have one, it compartmentalizes into the estimator part and then the resampling part, and you give it the estimator you want, tell it to bootstrap sample and give it the number of samples, give it the type of confidence interval you want, either quantile or whatever, and it spits it back, right? That's how it works. And so it'll work for any general, it'll at least return a number, it'll return a confidence interval for any algorithm that you can apply to data. There are modifications that are important, like if I don't have IID data, let's say I have repeated measures data. I randomly sample people and I follow them over time, and I'm including those repeated measures in whatever estimator I'm using. Then you don't randomly resample observations, you have to randomly resample people and take all their observations, right? It's called the cluster bootstrap. That's a minor modification, but then it will give you a non-parametric estimator that accounts for the fact that these data are not IID, but they come in clusters of individuals in this, or clusters of observations with an individual. And of course, you can generalize that to, let's say, I randomly sample classrooms and I have all the students in the classroom, then I would randomly resample classrooms. And you could, in some circumstances, also, if I randomly sampled classrooms and then randomly sampled students within classroom, you could have the nested bootstrap. You randomly take classrooms with replacement and then randomly take the students within those classrooms with replacement. You can make this as elaborate as you need to mimic the original design. But the whole idea is whatever you did in the design, you make the bootstrap mimic that. And therefore, you're getting the variability for that actual experiment conducted. A lot of times, some compromise is made because it's impossible to mimic it by some set algorithm, et cetera. But that's the basic idea. Does everyone get that? I mean, you don't really have to learn new kinds of bootstraps for these situations. Just realize you're mimicking your design, write it to repeat your design by sampling randomly from the independent units. If you don't have independent units, there's no simple bootstrap. If I have one big correlated network, not obvious how you do the bootstrap. There certainly can be circumstances where you can derive a bootstrap method that might work, but it doesn't follow from this simple description. You have to do something else. So this implies there are some independent units in your data that you can draw from, much like we've done so far this class. Computing time, this used to be a huge issue when I first started, and you have to implement this in Fortran on a PC, and it can take forever. Back in the 1800s when I started programming this stuff. Now it's not, this is rarely an issue for typical problems. Typical, like, if I was doing this for logistic regression, I'm not saying you really need to. You can use the robust option, but it doesn't take all that long. For some of these highly adaptive procedures, we're using superlinear, it can just take forever. It just becomes impractical. You can't do it. Because every run can take 20 minutes. To do 1,000 times 20, that's a long time. And it can get worse than that. So there are computing time issues that come in that in order to implement this practically for things that, for estimators that take a long time, you have to start thinking about parallel computing and using the cloud computing. And it just takes you into a level of complexity that's harder to make it practical. People do it, but it's not as easy. Anyway, that's one problem. I'm not sure it's a more serious concern. It is a more serious concern in the sense that, at least in theory, I could do it, a bootstrap on a situation where it worked, even if it was slow. But there's some situations where, in theory, it doesn't work. And it does rely on the same asymptotic linearity, the proof of the bootstrap working. So if the bootstrap, if you don't have an asymptotically linear estimate, there's no guarantee that the bootstrap's going to work either in deriving a confidence interval. So it's not like you can do it mindlessly. There are circumstances where the bootstrap really does not work, and they're easy to understand, but there's also general theory that tells you when it works. Practically, when you implement it, there are certain circumstances where you can know, like, I have to be afraid to use the bootstrap in this context because there's a good chance it will fail. And it really fails often in this context. If I change the data a little bit and it changes the estimate a lot, so that's what this is saying. If I'm going from here to here, and I have a large sample size, right? So I'm close to P0. So I'm getting close to P0. If I change Pn just a little bit and I get a very different estimate, I add a little noise to some of the observations, that kind of thing, that means it's not very smooth. And Bootstrap only work if it's pretty smooth. That is, it changes smoothly as I change the data smoothly in some abstract way. And you can think of it more concretely as adding little noise to, let's say, the outcomes or whatever you want to think about it. Some perturbation. Then it fails. Because and that's also related to not being asymptotically linear. Also, things that use algorithms that themselves use resampling, and that often means they're very sensitive to ties. Like ties have a big difference. The Bootstrap will fail. So, superlinear use cross-validation, right? And if I take random sample of observations and I ignore, and I'll get ties, right? Because that's what happens. I may get the first observation none, the second observation 3 times, the fourth observation twice, etc. Right? You get ties in your data when you randomly sample it. If those are broken up into different validation and samples, when you b-fold, you're going to have the exact same observation in a training sample and a validation sample. And what happens is your procedure will start overfitting. You'll get a distorted estimate of the fit now because it's trying to match exactly this observation to that observation. You can imagine like a procedure like nearest neighbor. Nearest neighbor just takes observations that are closest with regards to the covariates, and it takes the average of the outcome. But if it finds that you can do a perfect job by having an average which is just taking ones that are exactly the observation itself, you're going to converge to an estimate that's way too adaptive. It's way too rough of a model because of this resampling problem. So it's an example of when it starts to break down. That the Bootstrap will using Bootstrap to resample will not mimic what happens if I go back into the target population because those ties have such a big impact, and there is no ties in the target population. So those circumstances are where the Bootstrap starts to fail. And that's where, in those circumstances, the influence curve method may still work. So there are circumstances where the influence curve will work and the Bootstrap will fail. But there are circumstances for which your data, your sampling distribution isn't quite normal yet. If you look at the Bootstrap distribution, it's a little skewed. And the influence curve-based method relies on that normality, and the Bootstrap has this property where it can pick up so-called second-order departures from normality. So the confidence interval, it isn't really normal, and if you use the quantile method, it may pick up the fact that you're not, may give you a confidence interval that accounts for that more better. It's hard to know when, like I can't give you a rule to say, oh, the Bootstrap will be better here, but Bootstrap's a good thing to do often because it's kind of a diagnostic tool. When you do it, and you look at your distribution of estimators and you can see there's wacky things happening, you're like, okay, something's wrong. I have to look and find if I have weights that are too small or something that's making this highly unstable that you don't necessarily see from the influence, just using the influence curve alone. So but it probably means neither of them are working in that context. They're not giving you real confidence intervals. And you just have to be aware of that. That sample size is relatively small for the complexity of your problem. The Bootstrap may help you if you have departures from normality, but it isn't guaranteed necessarily to be any better than using normality. It could be that you just can't have accurate inference for that finite sample. Yeah?
Could you say a bit more about why the Bootstrap relies on the assumption that estimator have to be asymptotically linear? Why it relies on that?
I'm not going to do that right now because that's a fairly theoretical condition to go over, other than the fact that it has to be smooth. So if the Bootstrap doesn't give you a accurate confidence interval unless your unless your estimator is asymptotically normal. So it's not guaranteed to work if in fact your sampling distribution isn't normal. All right? And that condition right there would mean your sampling distribution isn't normal. So you can think of it that way as well. There's no theory that says using the quantiles when it's not normal is going to always give you an accurate confidence interval. It is not the same as sampling from the true distribution. It is an approximation, and the approximation is only good if in fact you're already in asymptotopia. It's used from departures from normality in an ad hoc way. And that's why I think of it as sometimes a more sensitivity kind of analysis where, yeah, I may report these, but I have to give caveats, say in fact the distribution, sampling distribution from the bootstrap doesn't look normal, and you have to take it with a grain of salt when I'm giving you. That just happens. But that's the main reason it has to be relatively smooth with regard to small modifications of the data, and if it's not, then it implies it's not normal yet, and that means none of these things work. Yeah.
In terms of the ties, would it be better when we're doing the cross-validation folds to assign each?
Yeah, that's a very good point. In fact, I have a student working on generalizing the bootstrap in various ways, and one of the ways that you can create, because the bootstrap, it's easy to show the bootstrap fails miserably, and like using superlearner for a substitution estimator, you can just show it fails by having procedures in there that are super adaptive like random forest. It just screws up. But if you guarantee when you take a random sample that all the observations that are ties are in the same fold, it gets rid of the problem. And that's no theory that says it will, it just practically does. So there are fixes that one can do for each of these that start making the bootstrap more attractive again. But it's hard for me to give you a universal endorsement because you can only prove that by simulation across a wide variety of data generating distributions. We don't have a proof. Is that what you were going to say? I'm sorry, I cut you off.
Yeah.
Yeah. Okay. Yeah, but it's a good.
Right
It's
now,
a.
that algorithm doesn't do that.
It's an excellent point. I mean, because so far practically that has worked extremely well. And it's kind of saved the bootstrap when you have procedures that use cross-validation within it. So. Yeah, I just talked about this. I mean, again, it's not a bad thing to do when in fact it gives you when you just use the, you get a sampling distribution back, right? I can draw a histogram of all my estimates. So this is like theta P and B. And, I could just, if I do 1,000 of them, I can make a histogram of where they are and take the two quantiles, right? 2.5 and 97.5. That's the idea. These would be the confidence interval. No, when it matches what you would do if I just did plus or minus 1.96 times the bootstrap standard deviation of this. If they don't match, these two, it could be you really don't have a normal sampling distribution. And so maybe the bootstrap is a little bit better way to do it, particularly if the confidence intervals are bigger in the bootstrap. You want to be more conservative when you don't really know if you have an accurate confidence interval, so you take the bigger one. At least you're more likely to be conservative, which is usually the goal when you have this kind of uncertainty. So it's not like you can't do it, and it's not a very useful tool, and sometimes there isn't an option. I mean, if I'm going to get a confidence interval for a substitution estimator, working someone that refuses to do TMLE, and it happens, they're just like, I'm not going to do it. I can't explain it, I don't understand it, I can run this regression over and over again, I can get these estimates in the bootstrap. I can do that, but I want a standard error. I tell them to do the bootstrap, given the caveats that I can't guarantee it's working, but it's something, right? It's some measure of uncertainty. It's probably not crazy, right? It gives you some idea of whether the estimate's highly variable or not. The confidence interval is probably useful compared to no confidence interval. So it's not like I typically in practice am nihilistic about this. It's just that I can't give good theoretical support that this confidence interval is going to give you the proper coverage, right? So you have to, balance these things in practice often. Okay, we've gone over this. I mean, we've gone over this too. It's just, sometimes it works, sometimes it doesn't. For the estimators we're talking about, where there's highly adaptive stuff, and if we're using cross-validation within our procedure to select a model, chances are you want to avoid the bootstrap. That's just a good, if I can give you one message, you want to think about the theory, that's a good one to have. You want to use more influence curve based. I have to say the influence curve based inference, because it's so it's computationally cheaper, is starting to take off in the big data world where they have sample sizes of 1 billion and they can't do bootstrapping. So this has been somewhat relatively obscure topic that we concentrate a lot in our division because we think it's a useful underbearing for developing theory, et cetera, is becoming more widespread because of practical concerns with computing. That bootstrap is becoming impractical for big data, precision medicine problems, things where you have millions of observations and very complicated procedures that take a long time. You can't do it. But if you can derive an estimator that has an influence curve, it's no extra time because once you're done with the estimate, you have all the influence curves. You have to have them to get the estimator. So I would just say for practicality, it's becoming important and it's getting wider usage as more people learn about it. And so this brings us to why do we need other estimators? Why not just a substitution estimator? Well, obviously, we want to have inference, and inference is crucial for most of us and the things we work in. And it's not necessary, there's no guarantee that more approximate inference using the bootstrap in circumstances where it theoretically can fail is not going to be completely misleading. So we can avoid it, it's a good idea to avoid it and use something we can rely on better. They both rely on this, so in this sense you can't really distinguish between them, but when that's the case, this one can still work when this one fails, and that has to do really that more general idea that sampling from the empirical, from your data, does not mimic what the variation in the samples that you see out in the target population. One very simple way to understand this is think of the asymptotics of it. If I have a sample size of 10, and I'm getting, let's say I have an Y, A, and a W, and W's are continuous, et cetera. If I take repeated samples of size 10 from the target population, there's never going to be a tie. But in my bootstrap samples, I'm in a super high proportion of ties. That sampling distribution is going to look nothing like the true distribution. So just that sample size example just tells you like it's not always going to work, right? Sample size has to be large enough, of course, where the sampling from the empirical is like sampling from the target population, and that certainly breaks down at small sample sizes when those sampling distributions just look very, very different. So this is a conundrum. This is the main conundrum that has driven our research, is that we don't want to rely on misspecified parametric models just because they're convenient and they're theory associated with getting inference if they're true, because they're not true. And in many cases, you're going to derive estimates that are just biased, and they're not using the data efficiently, because there's a lot of information to get out of it that you're ignoring because you a priori assumed a model. However, there's a lot of convenience that comes from it. That's why people do it, right? I can read a standard error from output. That's a lot easier than the stuff that you're learning in this course. So we really would like to develop estimators that are much more automated, that are based on good theory, that are only constrained by the knowledge that you actually have, that have things that can explore the data very efficiently and come up with reproducible estimates that can be done in a very automated way. But we need those estimators to be able to get inference. And it's not obvious when you start this, when this whole process started, that you could ever derive inference for these kind of estimators. So you were stuck between bias with inference, which doesn't really help you that much because you're going to need inference around something that may just be a nonsense, versus something that might be converging to the truth but has no inference. And that doesn't help you that much either because you don't know the uncertainty. So that led to explore other ways, other estimators than the simple substitution estimator. Much of is when we're doing the superlinear and we're using that to get a substitution estimator, I would think that typically would do better than just picking an arbitrary parametric model. but it isn't doing optimally for getting an estimate of the particular parameter. That superlearner is getting the best job it can do predicting, and sometimes that is not, that will contradict the goal of getting the best estimate of the causal effect. They're not necessarily the same thing. As sample size grows, they kind of converge, but for finite sample, they can be different things. A very simple example is I may have a confounder that doesn't add that much to prediction, but it really changes the estimate of my causal effect. And you can, in a finite sample, that can happen. In a big sample, if it doesn't have a big impact on prediction, it probably also doesn't have an impact on confounders. In a smaller sample, it can. It could be the variance bias trade-off for prediction suggests I should get rid of it. That the stepwise procedure will not choose that covariate because it's not really increasing the ability of the model to predict. But it's going to therefore introduce a bias in the estimate because you're leaving out something that's truly a confounder. And therefore, that procedure, that optimizing prediction is actually hurting you with regard to explanation or estimating the causal effect. You want to have procedures where the estimator is using the selection process to target what you want, not something that's just being used to get your estimate of the causal effect. And we haven't got there yet, but we'll talk, that's what we're going to get to when we talk about particularly TMLE. So at this point, even if I use superlearning, which I think is progress, it's not progress enough because it's the wrong variance bias trade-off for reasons I just said, and of course we've been going over this. There's no way necessarily to get accurate inference about it. And of course, this is a big problem in general that I'm less of an expert on, given my publication record. It's convincing people it's a good idea. People are really reluctant to use black boxes for estimation. I'll just talk about this for a second because it's kind of important if you are interested in this or you're going to use these tools, and I really believe in them, not because it's just some intuitive belief. It's because theory supports that things that we're going to talk about should do on average better than other competing procedures. But the problem is having a separate procedure for everything you're estimating from the same data, and particularly procedures that are black boxes, has a real psychological barrier to get over. People want to get that estimate of the effect, and then they want to see the whole model. And they say, well, what else is related? How is it related? I want to see it, right? I want to look at that regression, look at the coefficient, look at other coefficients. They want all in one. They want a big prediction model that also gives you the causal effect in one fell swoop, and one thing that can be seen tangible. There's no way to do that at this point where you do both optimally. If you want to get something where you can interpret the coefficients in some way as causal effects and be able to have a single model that also does prediction, you're going to be making compromises. And the main compromise is I have to have a functional form of this that's convenient to do, which means I'm going to be adding bias, right? I'm going to have to just assume it's a main effects linear regression model or main effects logistic regression model, or I can do something stepwise. But whatever it is, I'm going to be making that compromise. And the compromise is, of course, I'll be introducing bias into the estimate that way. So you have to be able to convince the reader that one, I'm not targeting the entire model, I'm targeting the estimate of the causal effect. And I can't do a better job doing that than if I use this particular black box called the superlearner, combined with other technology we talk about in the future. But what we have not developed in our group, and really I think remains as an open question, is how you, once you do that, show people why the estimate worked well, use the data in an exploratory way to show why maybe a traditional approach failed, have better kind of exploratory visualization, et cetera, so that this estimate, so why, let's say, an estimate that I use basic regression on is so different from something that I use machine learning. No one's going to be satisfied just showing that it's different and saying, oh, it's better in theory. They want to know, what is it about that? What did it pick up that the other one didn't, right? That's crucial. And I have students that work on these kind of problems in a more ad hoc way here and there, but it hasn't been a big push for us, and I think that's the remaining thing that's going to be needed to take this into a more wider distribution. It's growing in use for sure. It's spreading to other programs and people are using it. more and more. But what's missing is that communication with the reader to say, to bring them along, and also convince yourself that in fact, when if this is finding something that's very different than what I would have found and using something very standard, I understand why. It's because it picked up an interaction or something that was not there before, or whatever it happens to be. And yeah, any ideas on how to do that are appreciated. I think it's an open topic of research and an interesting one. I mean, I won't. So, how to proceed? Well, we're going to talk about TMLE, and TMLE is a way of using superlearner, still deriving inference, and it's a way of smoothing that original estimator so it has those properties we want. It's asymptotically linear. It has an influence curve. We can get inference for that, and that's really the goal. Is we want an estimator again that can be like a black box, but it's a black box based on good theory that works well in finite samples. Yeah, and I went over these, so that's it. That's it for this. Any questions? Okay, maybe I should ask you a question then. So, what's the problem with using the superlearner and creating a substitution estimator just from that, using the predictive value for different A's and taking the average? What are the two big issues?
It's the wrong bias variance trade-off.
That's one, wrong. So it's not targeting the parameter of interest, so you might have a good prediction model that's not very good for estimating the causal effect and an inference, right? So those are two major issues. What we're going to talk about next is, and I think I'll stop after this today and we'll talk about this next time, but we're going to talk about an estimator which is not TMLE, which is called inverse weighting, inverse probability of treatment weighted estimators, which does have the properties that it's asymptotically linear, and it has some virtues relative to the simple substitution estimator. It also has some pitfalls, which we'll talk about. And then we'll go to TMLE, which is really kind of, in a very rough way, a combination of both the substitution estimator and the inverse weighting estimator. And it uses virtues of both of those, and therefore is a more robust estimator. So I'll start that on next Monday, and just adjust the schedule accordingly. Sound good? Okay, thanks.